Now, we introduced the idea of sequences, that we can have, by some rule, a sequence of numbers in a list, and the idea that actually n can be imagined to go to infinity, and that's our sequence. But a series, and we introduce sequence really so we can get on to series, and that's the sum of a sequence. And if I was to stop here, this is known as a partial sum, because n was not allowed to go to infinity. But we can also imagine that we include an infinite number, so we get up to n with n is going to infinity. And in this case, this whole infinite series is we could try to calculate and say, hey, does this go to a limit? And if it does, it will call it L. And we can think of these series that they might converge or they might diverge. Okay? Well, let's start with a classic example of a sequence, which is each term is defined as n minus 1. So we start out with 1, 2, 3, 4, and we'll plug in some values here. For 1 minus 1 is 0, 1/2 raised to the 0 power, and we get, that's 1. And then we get, when n is 2, we get 2 minus 1 is 1, 1, this is 1/2. When n is 3, this is going to be 1/4, and you can convince yourself of that. Now our series is going to be now, the first element is 1, the second we're going to have 1 plus 1/2, the first term and the second term, and then we're going to have 1 plus 1/2 plus 1/4, and this sums up to 1, 1.5, 1 3/4, like this. We can also think of this as a something approaching a wall at 2, and we start out and we go halfway, we jump 1, and then the next step, there's our first jump, the next step we go halfway, we add a half, and we've still got a half to go. The next step we add a quarter, we go halfway by adding a quarter, and then you can imagine the next step we add an eighth, the next step we add a 16th, the next step we add a 34th, etc., etc. And finally, what we find out the answer is, at a limit, is we approach 2. And in the book, it has a whole little section here that talks about doing just that sort of analysis.